Hello, everyone. Thanks for joining in with us today for our topic, using testing and diagnostic methods to extend the life of cable systems. My name is Michael Fleischer, and I'm the Marketing Communications Manager for Megger here. I'll be acting as the moderator and helping you with any technical questions or issues for our presenter team. On the left side of your screen, you'll see our Ask a Question window. You can submit questions at any time during our presentation, and I'll read the questions out during our Q&A segment at the end of the webinar. That box looks like that. I've just pushed that to our slide. Our presenter today is Yash Gadwani, Applications Engineer. To assist with the question and answer segment at the end of the webinar, we have Chase O'Veal, Applications Engineer, joining us. I'd like to remind everyone that after our Q&A segment, we'll be sending out your certificate of attendance, a copy of the presentation, and a link to the recording of this webinar. Typically in about 2 business days, we aim for about 24 hours after we conclude. Additionally, the link you use to join into this webinar will become a recording link an hour and a half after the webinar concludes today. So with that, I will throw things over to our presenter, Yash. Yash, thanks so much for joining in with us today.
Thank you, Michael. So I'll just quickly introduce myself. My name is Yash. I'm one of the applications engineer with our technical support group. I've been with Mega for about 5 years. I have my BS and MS in electrical engineering. Without further ado, I'll just jump right into it, and I'll switch off my camera just to save some bandwidth. But yeah, we'll start the presentation. So, today's topic is using testing and diagnostic methods to extend the life of cable systems. We often tend to forget cables as our key assets. Everyone thinks about transformers, circuit breakers, and whatnot in the substation, but often cables are one of the assets that tend to be forgotten. And in the recent times, people have been catching up to speed to the newest technologies and test methods that have been into the market for cable testing. And a lot of interest has been towards online monitoring and partial discharge. So we'll cover that as well in this presentation. So for today's agenda, we have a little bit of basics, theoretical approach on how to tackle cables. We have to understand cables and how their structure is before getting into the parts of testing. What are the different aging conditions that they see during their lifetime, as well as what is the modern withstand testing, how do we do it, what are the parameters associated to it, what is our end goal after the testing, how do we evaluate the results and interpret them, a little bit about tan delta testing as well as PD testing. So, jumping right into it, uh, to understand cable testing, first we have to understand what is the basic structure of the cable. Because I'm going to reference a lot of things from here, so it's important to know what am I talking about, and this helps you kind of visualize a little bit better what testing are we doing and how does it affect the structure of the cable. So that's your typical cable. You have your center conductor, you have your conductor shield, you have your key insulation or your main insulation, and then you have your insulation shield, metallic shield, and then you have your outer jacket. Now, this is just a general structure of the cable. You might not see this kind of structure every time, but this is just one of the most common ones that usually people tend to see in the field. And there's a couple of different types of cable that come into mind when we say, hey, I'm looking at cables. So there's EPR, XLPE, PILC insulation cables. There's different kinds of conductors inside the insulation. So if you have 3 conductors inside the main insulation, that's also something that is to be kept in mind when you are testing. You have something like that, or you have a triplex cable. So these are all the parameters that will come into picture. So it's important to know what kind of cable that you're dealing with before jumping into testing. especially just to give you a rough idea that PILT cables usually have a lot higher breakdown voltage than your normal EPR or XLPE. The reason being that PILT cables have insulation medium as oil because the paper that is used for insulation has oil impregnated into it. So their breakdown strength is a lot more higher than your normal EPR or XLPE type cables. So that kind of gives you a little bit of background on why it is important to know what kind of cable that you are testing. And cables during their lifetime have a lot of different stresses that they see during their whole life. Like let's say, for example, thermal stress, electrical stress, mechanical stress, or environmental stress. The key ingredient to failure is once these stresses surpass their limits and they tend to break down the insulation, and ultimately you have a failure in the cable, right? Why do we do the testing? To increase reliability of the system, right? To reduce the number of outages, basically our SAIDI and SAFE index. Because if you are, let's say, utility, then obviously these indexes matter to you. You are penalized if those indexes go above a certain number. So definitely you want to make sure that you are at a minimum number of outages during a certain amount of year. Proactively repair or replace the question. Obviously, you want to make sure that your system is every time reliable and it is operating as it's intended to be. And instead of replacing cables by age, this gives you a more targeted repair that you only replace the cables that need repair. Ensure there are no defects in manufacturing or workmanship. So obviously, whenever you splice a cable or you have created a new cable and you're installing new terminations, you want to make sure that everything operates as it's supposed to. It's not like you're um, pulling the breaker and the next thing you know, it did energize and you have a failure in the cable. So that's something that we don't want. That's why we want to test and make sure everything works before we kind of put actual load on the system. And third thing is catching the aging conditions before they actually fail in service. So this falls under predictive maintenance. This is what everybody wants to move towards ultimately, because you want to actually make sure that you don't have a failure in the system. You can predict those failures before they actually happen. Now, what does IEEE recommend? IEEE 400.2 is the standard for VLF testing, and it typically recommends that you do a 30 to 60-minute VLF test, and there's three different voltage levels that you have to follow depending on what kind of testing you're doing. So either it's installation, that is tested upon delivery to make sure there are no damages during shipping or there are no gross defects that came from the manufacturing side of things. Once that is done, you can do acceptance testing, that is upon completion of work, but before being energized. So you are making sure that your splices, terminations, accessories, everything operate and survive as they're supposed to. That's acceptance testing. And then you have your maintenance, which is regularly scheduled condition check of cables, typically done every 3 to 5 years to ensure there are no like developing defects in the cable. And then it also kind of gives you a good idea about the health of the cable. So those are your three different voltage levels: installation, acceptance, and maintenance. And also, you want to make sure if you performed any repairs on the cable, you want to make sure that it is holding the voltage and there are no workmanship issues. So there is no specific standard around that, but typically people tend to say that, hey, I'll just do a 5 minute quick VLF or 10-minute quick VLF just to say that, okay, everything works as it's supposed to, and now I can put it back into service. So I've been saying VLF a lot. What actually is VLF? VLF stands for very low frequency, and it's fundamentally AC over voltage test, just like a pressure test. Um, it is performed at zero point 0.1 hertz as opposed to your normal power frequency that is 50 or 60 hertz. I will give you the reason why that is in the next slide. Um, it is basically like a pressure test. You are applying a voltage above your operating voltage as described by IEEE 400.2. Like we said earlier, it has three different standard of voltages: installation, acceptance, or maintenance. Depending on what kind of testing you are doing, you will say, hey, if I'm doing maintenance testing, I will apply 1.5 times my operating voltage. So that's how VLF test works. And basically, you're looking for a breakdown if your cable passes or fails. But this VLF test has a very limited diagnostic information. So it's basically like a pass or fail test. Either it passes or fails. That's your kind of end result. But if you want to do more diagnostic tests, then you can either jump to PD or 10 delta, which we'll cover later in the presentation. Um, so to give you a background, what was used before VLF came into picture? DC test sets were used for many, many years. A couple of utilities or a lot of customers still out there use DC test sets because they are small, light, portable, and inexpensive, right? Easy to manufacture, cost-wise, they're very effective. So they have been used for generations. But the cables of those times, like before 80s, 90s, all were mostly built cables, and their insulation characteristics are a lot more different than your modern cables that are typically extruded. That is your XLPE or EPR cables. Now, extruded cables behave different than laminated because extruded cables can develop trapped space charges when you are injecting DC into them. Because if you look at DC doesn't have a frequency. So you're just injecting a single polarity into your cable system. Let's say if you inject a negative DC voltage, then it will trap those charges in those voids or insulation defects. And then when you energize it back with an AC, AC has dual polarity, positive and negative. So whenever that those two polarities meet, it kind of creates a pinhole fault in that cable. So that's why extruded cables have a little bit more different characteristics than your laminated cables. And this is also proven by the EPRI study that is referenced here. So I'm not saying things that just came to my mind. This is actually a scientific research that was done by the EPRI Institute, and it proves that can reduce your life of cables because of those trapped space charges. And another reason why we don't want to use DC on extruded cables is it is blind to certain defects. I'll cover it in the next slide that what defects is it blind to typically. Uh, so let's just look at that. If, let's say, in this example, they created an artificial needle fault. So what they did was inject a needle halfway through the insulation, and then they created a flashover point at this end here, and it basically stresses out the insulation at that point. Uh, and now they're using your 50 hertz AC, that's your reference signal, or your normal voltage that a cable will see through its life. 50 hertz because this was done in Europe. here we have 60 hertz. So this is just happens to be that it is done in Europe, so they used 50 hertz. VLF sinusoidal, this shows you the level of voltage that they use. 3 times U naught being your operating voltage. So 2 times your operating voltage, 3 times your operating voltage, that kind of thing. And the duration as well, how much time did they do it for, and the test objects and the fault occurred. So 10 out of 10 faults were found in 50 hertz. If you look at VLF sinusoidal, they found 5 out of 5 faults. VLF cosine rectangular, they found 5 out of 5 faults with 3 times the operating voltage here and here. And even if you use 8 to 10 times DC in terms of operating voltage, they could not find the fault in that case. So it is blind to certain kind of defects. That point being, similar to the example here, they did an artificial wet fault where they seeped in some moisture into the insulation. Likewise, you see here, it's a water-filled hole basically, and you have the similar kind of results here as well. That effects were found when injecting 8 to 10 times operating voltage, right? So it then this is the source where the study was conducted. It was a paper written by these gentlemen listed here, and this is what they found out, that this is what happens inside the cable when you're injecting DC, and they just reference a couple of different voltage waveforms that they used in this study. Now, 400.1, that's IEEE 400.1, is the DC guideline for using it on PIL cables, that paper insulated lead covered cables. And they specifically state that this guideline is only for laminated power cable, and this is not for extruded cables. No IEEE or guide exists for DC testing on extruded cables. So that's something that is to be kept in mind. And most of the modern cables are either XLPE or EPR, which we call extruded cables. So if we can't use DC, then what option do we have? Either we use AC, 60 hertz power frequency, or we can use 0.1 hertz VLF. Now, what is the advantage when we use 0.1 hertz power frequency is you are reducing the power by 600 times, and that's what allows the test sets to be more portable. So that's your main advantage. Just to give you a visualization, if you were doing 60 hertz testing, you would need a truckload of equipment to do a similar kind of cable that's given here. You're doing a 15 kV maintenance test with a capacitance of 100 picofarad per feet, and the cable length, let's say, is about 1,000 foot. You would need 9650 VA, that's your power, to do that 60 hertz test. Versus when we are doing 0.1 hertz test, you would only need 16 VA, which is much more practical. So your test set can be a lot more smaller and compact compared to a 60 hertz test. So that's your main advantage of doing a VLF test. Next is when you look at values that are supposed to be followed, this is a table from IEEE 400.2, that's your VLF standard. That gives you, like we said, 3 different voltage levels, right? Installation, acceptance, and maintenance. And each one, it is clearly defined what voltage level do you need to follow. So this is only a partial snapshot of the table because it covers from 5 kV all the way up to 69 kV cables. So it does tell you what voltage you should do your VLF test if you're running either acceptance, installation, or maintenance. It also tells you about cosine rectangular waveforms, which we'll discuss a little bit later in this presentation as well. So, what are the different aging conditions that a cable sees during its lifetime? It, one of them is water trees. This is a typical example of water trees. This is something that develops from the outside of the insulation towards the conductor. So once moisture seeps into your insulation, it kind of develops these water trees over time. Three key ingredients for this recipe: voltage, moisture, and time. Right? It doesn't develop overnight. Obviously, once the cable is in service for 5 years, 7 years, 10 years, whatever that time would be, that kind of gives that cable that seeping moisture over time. And it has lower resistance than your insulation. So typically, that kind of develops a stress area at that particular point. Or now, if we are looking at electrical trees, which are typically growing from the conductor towards the insulation that is pointing outwards, or they can also develop in trapped space charges, or if you have voids in your insulation, then they kind of tend to grow electrical tree over time through partial discharge. And they are conductive. So obviously you have electrical current flowing through them, and that's how they kind of progress over time. And electrical trees grow very much more rapidly than compared to a water tree, because electrical tree you will have days to catch it or hours to catch it before it kind of progresses into a fault, versus water tree, it is very likely that you will catch it in your maintenance cycle. Now, when that happens, that electrical tree meets a water tree, you basically have a bow tie at this point, and it kind of tends to create a pinhole fault in that case, and it will develop a fault. So, that is a typical kind of picture that I like to show, that this is what happens when both of the electrical trees and water trees meet at a certain point or interject, and then you have your fault creation. This is just a good example of what kind of electrical trees and water trees are critical. So these this red line shows that this is the limit for trees from the inner semiconductor. That is, if your water trees have grown past this red line, then that is likely to fail in service. And this is the water tree that is a critical size growing from the outside towards inside. And if it has surpassed this blue line, then it is likely that it will fail during service. And this is just a good representation of what is a critical versus a non-critical water tree. And the total length between your center conductor and your outer jacket is 4.5 millimeters, and that shows your length of insulation. Now, just to see what is a local issue and what is a global issue. So let's say if you have a termination issue, that your termination kind of failed at that point, that's typically a workmanship issue and is localized to a specific spot in your cable. Whereas water tree and such is more like a global issue. It is spread throughout the insulation. It is not at a certain point or anything like that. You pretty much have growing water trees all over the cable because of moisture seeping into the insulation. Joint or splice, that is also more of a local issue. If you have certain partial discharges, like you see in this picture, happening at that specific point, then it's more of a local issue. And weak spots, that is in either critical size water trees or electrical trees, is also a local issue. because this is a critical size water tree versus a non-critical water tree, right? Critical water tree is has a very high risk of failure in service, so that is a very localized issue at that specific point in the insulation. Or if you have electrical tree, that's even more so that it will fail within hours or days. So results, whenever you are doing a VLF test, at the end, if it holds the prescribed voltage for either 30 between 30 to 60 minutes, typically if it survives for the next 60 minutes, then statistically it's about 97% reliable for the next 2+ years. And I'm just not pulling this number out of anywhere. It supports that study, Dortmunder Energy and Wasser Experience Report. They conducted a study for the period of 1987 to 2007. So that's 20 years worth of data that 97% number comes from. Um, and that kind of proves that once you do a VLF test for 60 minutes, you have high reliability on that system for the next 2+ years. And if a cable breaks down, obviously now you have a faulted cable. So either you need to repair it or bypass it. So it's always wise to have CFL or cable fault location equipment on standby, or you need to have a backup plan in order to kind of bypass that cable, or a backup cable to immediately repair and put it back into service. So that's one of the things that we recommend, that you should have something on standby, that if your VLF test fails, then you have some backup plan to put it back into service. Now, one of the key things that come across is VLF accelerates the aging condition to cause existing weak spots to fail during the scheduled outage time. So it is preferable compared to an in-service failure, but a lot of people say that, hey, VLF caused these problems. Well, VLF does not cause those problems. Those were existing weak spots in the system that it caused by accelerated aging process to fail in that scheduled outage time, versus like they would have failed anyhow in service sooner or later. So you would rather have them fail when you are in an outage rather than having them fail in service, and now you have to send emergency crews, and it's just a lot of manpower and budget that goes towards those unexpected failures. And again, this is proved by NEAT track project numbers. NEAT track is one of the wings of Georgia Tech University, and they did a study on doing VLF tests, and they said it has no adverse effects on the cable life at prescribed levels. And they also concluded that IEEE 4.2 suggests that you should do acceptance installation or maintenance, and you should follow those voltage levels. And if that survives, then likely you would have a good cable for the next 2+ years. Now, what are the different parameters that play into picture when you are doing a VLF test? First one is frequency and your waveform that you are using to do a VLF test. Now you can either use a VLF sine or cosine rectangular. I know that it looks very similar to a square wave, but trust me, it is not a square wave. This voltage change right here, uh, that switch from positive to negative, it is a slant slope which mimics a 50-60 hertz polarity change compared to your normal power frequency. So it is not a square wave. It does look like that from far away, but when you zoom in closely onto that waveform, it is a 50-60 hertz change slope that is changing from positive to negative, and it kind of mimics that polarity change in a power frequency. The other thing that I do want to mention here, that sometimes what tends to happen is when you have a large cable, your frequency, zero point 0.1 hertz, might not be enough to conquer the capacitance on that cable. So, what do you do in that case? Well, there's an option to drop down the frequency from zero point 0.1 to even lower, let's say 0.01 hertz. So you're reducing your frequency tenfold more, which gives you a higher power to conquer that capacitance on the cable. So that is something that you can do. But in that case, your test time would be extended to typically tenfold. Now, if you're doing a 60 minutes test, you would have to do a 600-minute test, which typically is not a very friendly thing to do, right? You don't want to be sitting there forever to do the test, but sometimes they do it just to overcome the limit that is posed by the equipment itself due to the capacitance of the cable. The next two things that are determined at the time of test, this is typically determined by your equipment, your frequency, and your waveform. And once you are ready to test, and before beginning the test, it will ask you what voltage level do you want to use, right? So either you're doing acceptance, installation, or maintenance. Depending on that, you would select your voltage level 1.5, 1.7, or two times whatever that might be. And you have your test time, right? Either you want to do a 30-minute test or 45 or 60-minute test, depending on whatever your standards are. If you're following IEEE 400.2, that suggests between 30 minutes a minimum and 60 minutes. So anywhere between that time. Now, this is just again saying that if you use a lower frequency, uh, it is likely recommended to extend out your testing time in that case, and it is typically done to overcome the insufficient capacity of the test set. But in that case, you will have very limited data to compare to because there are uh, not very much out of results that you can go and compare that to. And this is again sourced from IEEE 400.2, what happens when you lower down the frequency. That is just an abstract from the standard itself. The two different parameters, waveform, sinusoidal, which is typically recommended for 10 delta testing. If you're doing 10 delta, then the only thing that you can do is sine wave. You can do a 10 delta with a CR or a damped AC. So that's your only option. You can also do PD testing with your sine wave, but cosine rectangular is recommended because it has easier tendency to excite those partial discharges when it comes to that. We are also going to cover that a little bit later in our slides. Cosine rectangular, it these waveforms can handle higher capacitances. So if you have let's say if you're doing testing on wind farm cables, which are kilometers or miles long, then typically you would have a very high capacitance that you are dealing with. And in that case, cosine rectangular can handle those kind of capacitances. You cannot use this for 10 delta testing because it can only be done with sine wave. It is recommended for doing PD testing because it has tendency to excite those partial discharges more easier compared to a sine or a DAC wave. And it can measure leakage current. So you will have a leakage current value in that case that you can correlate to what's my leakage current doing. Again, this is just voltage determination. This is determined by 400.2, and it covers up to 69 kV of cables. So this is pretty straightforward. You can easily do it. Now, just to give you a little bit of background on this here, distributions of failures over time. So somebody might say, hey, if I only do a 30-minute test, what is my disadvantage? Like, what am I losing if I don't do it for the complete 60 minutes? So again, I would like to cite this report, uh, Dortmunder Energy and Wasser Experience Report, that has 20 years worth of data. So this just shows you a distribution of faults over time. So typically, if a cable has to have faulted, it will fault within the first 10 minutes, 66% of the time. The next 75% failures you will catch within the first 30 minutes, and the rest is about in the second 30 minutes. So most of your failures that you will see, about 66% occur within the first 10 minutes of a VLF test. So let's say you are doing a 30-minute test, most of the failures you will catch are within those 30 minutes, right? So, and there's only a 25% chance that you might catch the next ones in the next 30 minutes. But sometimes what happens is if you're trying to grow a tree and, like, let's say a water tree is growing with that BLF test in the 30 minutes, and now it was supposed to be faulted on the, let's say, 40th minute, then you have already grown it to a level that it is now critical. But if you're removing that voltage, then it is kind of counterintuitive that in the next 10 minutes, which was supposed to fail, and now you have grown that tree far enough that it might fail in service. So it is recommended, depending on the cable that you're dealing with, how critical it is. 60-minute test is what a lot of people go for, or a 45-minute test, which is also very normal to see in the industry when you're doing a VLF test. And something that we did with TNB distribution in Malaysia, they had a cable replacement program, and they wanted to do a VLF test, and they wanted to do a health-based maintenance versus an age-based kind of replacement. So they tested about over 15,000 circuits, and they conducted over 17,000 VLF tests, and they found about 2,000 faults in the circuits that they tested, and only 11% of the faults were in the second 30 minutes. So most of the failures that happened were in the 0 to 12-minute mark, and the rest were in 13 to 30-minute mark. And then it kind of drops down even further when you move from the 31 to 60-minute mark. So that kind of gives you a good idea of how long should I run a VLF test for. So I hope that answers a lot of questions on your regular VLF test. Now, reliability data of cables after the test, data from TNV distribution again confirms those Dortmund numbers. Only 2.8% of the tested cables failed after they were put into service. So that 97% reliability, again, it confirms those numbers, and it is similar to the Dortmund numbers. So failed after the test, this is what you are looking at. Um, it is a very low number. So again, you have your good estimation that most of the cables that survive that VLF test are likely to be reliable. Now, what happens during a zero point 0.1 hertz AC withstand VLF test? You're typically converting your critical water trees into electrical trees, and if that was supposed to fail, then it typically fails within service. And it triggers partial discharges to happen within that environment. So if you are trying to measure partial discharges and you have your equipment conducted, then equipment connected, then you can also measure partial discharge along with your VLF test. And it accelerates aging in a controlled environment. And that just is, again, a picture of electrical tree and a water tree, and combining them kind of creates a failure. So if withstand test doesn't provide much of information on the insulation condition, what test do I need to run? Because we said VLF is only a passive fail test. So what happens if I want more diagnostic information about the test itself? Now, 10 delta is one of the tests that you can do uh, along with your VLF test, or you can also do a partial discharge test to provide local assessment of where those peak spots are and where exactly do my problems lie within. So this is a good analogy that I like to give people uh, to make sure they understand the difference between a VLF test and a VLF 10 delta testing. Um, let's say you go to the doctor's office, the doctor asks you to run on a treadmill. If you survive, you pass, or if you die, then it's a fail. So that's basically your VLF test, causing weak spots to fail during a controlled environment. And but it's a very black and white test. Either it's a pass or a fail, right? Now 10 delta compared to that is you can go to the doctor's office, but now you have a heart monitor attached to your chest, and the doctor asks you to do a 5 minute walk, a 5 minute jog, and a 5 minute run. So you're watching for the signs of stress as you kind of go through the test, and that's basically you're injecting VLF at your zero point 0.5 times U naught, that's zero point 0.5 times operating voltage, your 1 times U naught, that's your operating voltage, and 1.5 times U naught, that is half a time more than your operating voltage. So you're looking for signs of stress, that is basically your 10 delta. Then you're now monitoring everything that's going on within that test. What can it not detect? That's your limitations for 10 delta. It can only say whether there is a problem or not a problem. It cannot specifically say what the problem is. Is it a void or a water tree? I don't know. Cannot distinguish between major problems in a small section or minor problems in a large section. And this is all because the test is an average, or it's a global test, so it kind of gives you an overall number rather than pinpointing to a specific section. It cannot tell you whether there's problems in the jacket or shield. It is an averaging test again, so it cannot pinpoint to that section. And it must be a single type of cable. So different characteristics of different cable insulations mask certain defects. So if you're mixing XLP and EPR cables, then 10 delta test numbers would not make sense to you because your IEEE standard gives you a specific guideline. Based on this number, you should have a cable that doesn't require any more investigation, or it does require investigation, or there is immediate action required. So depending, and it is only made for specific installations. So if you're mixing cables, then you might be masking certain defects. Now, parameters that are supposed to be used in the 10 delta test, you want to make sure that your rated voltage of the cable is accurate, because that would determine your 3 voltage steps, because you're doing zero point 0.5 times rated line to ground, 1 times rated line to ground, and 1.5 times rated line to ground. So once you put your operating voltage in, the unit will figure out kind of that 0 0.5, 1, and 1.5. And there's typically 6 to 10 measurements that are taken on each voltage step. So you have your 0 0.5 step, 1 step, and 1.5 step, and it takes 6 to 10 measurements on each of those steps. And then it gives you average based on that. So you have your 10 values, and it will throw out an average saying this is your value at 0 0.5 times, 1 times, and 1.5 times. Now there's a couple of different parameters that are important during VLF test, 10 delta test. your stability, your mean value, and your differential. So there are three different parameters that are important during a tan delta test. It takes about under 6 minutes per phase. So once you connect it, it jumps through all these steps, and it is pretty fast or pretty quick test. So it is much less stressful on the cable, and it gives you some diagnostic information, and it throws out a number based on which you can make your decision. Hey, is this a weak cable? Is this a good cable? I can make my decision based on that. You have your steps right here, zero point 0.5 U naught, 1 times U naught, and 1.5 times U naught. This is your tan delta reading, 0.45, 0.65, and 1.0. As you see, it's climbing with the voltage. And this is your stability criteria. Stability just suggests that how much of your readings are changing along with your 6 to 10 measurements, right? You have your 6 to 10 measurements. If they're jumping across a lot, like on one step I have 3.0, on the other one I have 4.5, then that's not a good stability. My reading is jumping around a lot. So that is basically your stability criteria. And differential is your zero point 0.5 times U naught reading minus your 1.5 times U naught reading. Or I said it the reverse way, like 1.5 times U naught minus your zero point 0.5 times U naught reading. So that gives your differential value at that point. And based on these three different criterias, and you have your IEEE 400.2 table, it throws out that whether it's immediate action required, whether it's further study advised, or no action required. Based on that, you can make your decision. The advantage of doing this test is it's more than a go no go test. So it's able to monitor signs of failure. And if your 10 delta reading is increasing with the voltage, you may be able to abort the test before the cable actually falls. And you might be able to put it back into service for a short amount of time at increased risk of failures. Because the cable has not passed the test, you just decided to abort the test, and then you are making your necessary arrangements for your backup power, or let's say you want to return to that with more convenient time. 2 days from now, I will have my crews run out there. I'll have all the materials and personnel needed to do the repair in 2 days of time, and then I can get back to that cable, actually run through the BLF test as a whole, fail it under controlled environment, and then I will put it back into service by repairing it altogether. Now, that was all about tan delta test, and now we are coming to the most advanced test, that's your partial discharge. So what is partial discharge? Uh, it is like I had to cover BLF tan delta and partial discharge, so I apologize going a little bit too fast, but I only had a short window of time to cover all those three, and it's a lot more deeper than this that I can go, but unfortunately, because of time constraint, I had to run through a little bit of overall uh, because of that. So, what is partial discharge? Low energy dielectric breakdown, whether in air, that is corona, that you see on the picture here. It is a lot more visually appealing to see, versus in an insulation that is not visible, because it's happening inside a void or a discharge that is between the insulation, which you cannot physically see because it's all internal to the insulation. And it typically does not bridge to conductors. So it's only happening within the insulation. It's not being conducted or bridged by two conductors. It occurs when a voltage gradient or difference is present. So it does not occur during DC testing. The differences between small areas in the insulation. So you have your smaller areas uh, or voids inside your insulation where it typically tends to happen. Uh, that's what we exactly said. Where does the partial discharge occur? It occurs inside the insulation in contaminants and impurities, if there are any harsh bends, if there are any voids inside the insulation, or splices and terminations, if there's a proper cutback distance. Like in the picture here, you see the yellow mastic tape is missing on this kind of insulation. Then it's likely that partial discharge will happen on this kind of thing because it will lay more stress on the cable. And it can also happen because of misaligned accessories. So if you have something that's not sitting on the termination properly, or if you have air voids, I'll show here in the picture, like let's say if you have air voids here, then that'll typically tend to create partial discharge over time, and you'll have something like that occurring on the semicon layer. And over time, it will kind of keep eating your insulation, and as you go, it will fail your cable prematurely rather than having run through a whole life. So it is typically because of your quality of termination and splices that it contributes to a lot of PD, and it is very rare that it happens in the bulk insulation because in there everything is more manufacturing side standardized, and it is typically that you will have partial discharges on your splices or terminations rather than your uh, rather than your bulk insulation. So how to detect partial discharge? You will have your signal of breakdown from your partial discharge. Like let's say in the picture above here, you have your cable constructed, you have your splice in the middle here, and these are all these dots here typically relate to the partial discharge that is happening within that splice. And this shows your intensity of the partial discharge. So in this here, I know it's not very clear, but something around 4 nanocoulombs is your intensity of partial discharge. And this guy is your coupler. So this device is typically what measures that partial discharge coming from the cable. So how to test? Obviously, ensure your circuit is de-energized and grounded and follow your proper work procedures. You set up your power supply, your coupler, your grounds and accessories that are required to test that typically are shown in the picture below. And you apply your voltage to test your cable. Now, a lot of people have different ways of testing partial discharge. Uh, it completely is up to you how you want to test it. Sometimes people start from all the way up, that is 2 times U naught or 1.7 times U naught, and then gradually come downwards, that is 1.5, 1.3, 1.0, zero point 0.7, and zero point 0.8. Or you can also go zero point 0.5 and then upwards up to 1.5 or 2 times U naught, and you are injecting the voltage for a couple of minutes per step. So you are just giving partial discharge enough time to excite and show up on your system. And once you're satisfied with the result, you move on to the next voltage step. What do we look for? We are looking for a pattern, that is intensity and distance to the partial discharge. Higher intensity of events obviously indicates you have a gross problem. Excuse me. And you're looking for your inception and extinction voltage. PDIV or PDEV. If you're familiar with PD, then you might have heard these terms, PDIV and PDEV. So PDIV is your inception voltage. That is, when do partial discharge start to happen? This is important because if your inception voltage is lower than your operating voltage, that means partial discharge is present all the time and it's eating up your insulation pretty fast. You don't want your PDIV anywhere inside your operating voltage. Extinction voltage is when do these events disappear. That means if you're bringing your voltage down to 1.2 times your operating voltage and your partial discharge doesn't appear anymore, then it's obviously a good thing because your extinction voltage is higher than your operating voltage, and the partial discharge kind of stops at that 1.2 times, and obviously it is much more beneficial uh, to do that. And interpretation of results, there are a lot more parameters involved when you are considering interpretation of results. Obviously, we discussed inception and extinction voltage. Is PD only present above operating voltage? If yes, then that's a good thing because it doesn't come into your operating voltage. Whenever it starts coming into your operating voltage, then obviously you have a problem that partial discharge is happening all the time. Event count, that is, how many events of partial discharge did I record during that voltage step? So more events suggests aged cable. Obviously, if you have more and more events that are happening on each voltage step, then definitely you have an aged cable, and you might want to look into a good maintenance plan or good proactive repair plan. Event intensity, the greater intensity suggests the aged cable. Intensity means how high is my partial discharge. Let's say if it's higher than 700 picocoulombs or 1000 picocoulombs or 1500 picocoulombs, then obviously I have a problem in that case. Relative intensity of positive and negative polarity. So, if you're familiar with partial discharge, you must have looked at the PRPD pattern. That's phase resolved partial discharge pattern. So, that pattern can tell you if you have a lot of events on your positive or negative polarity, then if the partial discharge is present in the semiconductor or bulk insulation, or if it's more towards just a couple of different accessories. But that requires a lot of finesse and familiarity with partial discharge, and it is typically left for the user to interpret how to, have those results interpreted. But it comes with that experience. Obviously, when you start doing a lot of partial discharge testing, then you would get that experience that, hey, I'm seeing this kind of pattern and this kind of correlates to my semiconductor or bulk insulation rather than a splice. Now, this is just showing at different waveforms how does partial discharge happen, or what can we see in terms of different waveforms. So in this specific case study, we did three different waveforms. We have VLF sine, VLF cosine rectangular, and damped AC. So we'll see all of those three waveforms and how does partial discharge happen on them. This is 11.6 kV RMS cable. Length is about 1.3 kilometers. And you have a couple of different kinds of cable attached to it. In this picture, you can see these different colors represent different types of cable. So one might be XLP, the other one be EPR. So it's a mixed cable, and all these points, these little rectangles, represent a splice or a joint in that specific area. So currently we are doing VLF sine. I'm only using phase one, that is L1. My voltage is about, where is this? Yeah, 11.6 kV RMS. I did my PD testing, and this is what I see, that in here, in this specific splice, I have a lot of partial discharge coming from that. And the level is about, the highest that I see is 250 picocoulombs in VLF sine waveform. Now, compared to this, let's see what do I see in my cosine rectangular, right? Or damped AC. So here we did damped AC, and we see a lot of partial discharge, which is at a much higher level than your VLF sine, because again, damped AC is much more provides much more excitation to the partial discharge compared to your sine wave. You see the intensity of partial discharge here, and this was the one that is happening here was not even visible on the sine wave. So it gives you a much more level of partial discharge as well, 250 picocoulombs versus now you have 1500 to 1800 picocoulombs, somewhere in that range. So it gives you much more visibility in this case. And we are going up to all the way 1.9 times U naught, that's your operating voltage. So you see partial discharge here, you see partial discharge here, and the level is about 2000 picocoulombs. So obviously that's indicating to a very good problem there. And now we are analyzing results, same cable, same everything with CR. That's your cosine rectangular. Now you see a lot of partial discharges here, here, as well as along the length of the cable. Um, and the intensity of partial discharge is also very much more higher. It's about 4000 picocoulombs because of again the excitation voltage that you're using. So it is easier to see the partial discharge with a CR or a DAC wave compared to a sine wave. Now, someone might ask, well, what is the guidelines for either XLPE or APR cables? Um, for XLPE and APR cables, here's your kind of rough guidelines. For if you have a newly laid cable, it should be PD free to 1.7 times U naught, that's your operating voltage. And if you have an aged cable, then that's your kind of level of partial discharge that is allowed for at operating voltage. And this just gives you kind of, if you have partial discharge uh, between this and this, your PDIV is your inception voltage. So it starts to occur between 1.3 to 1.7. That typically your next recommended PD measurement is between 3 to 5 years. If you have something between your operating voltage to 1.3 times operating voltage, do it every 2 to 3 years. If it's less than your operating voltage, do it every year. So that kind of dictates your guidelines for XLPE or APR cables. And this is for guidelines for PILC cables. So you have your PILC cables. That's again your guideline. I'm not going to read through it, but just uh, given that it fits a H cable, your joint or insulation should have less than 10 picocoulombs of partial discharge at U naught, that's your operating voltage. And you will get a copy of these slides, so you can just reference it back here whenever you're looking at those slides. Now, that being said, that kind of concludes my presentation. I'll just go through a little bit of equipment slides. What does Megger have to offer in terms of solution to all of this? We have a PLF sinus unit that's 62 kV. It's also available in the variants of 45 kV as well as 28 kV. These units are smallest and lightest units on the market. It has a huge touchscreen with color display and everything. It has automatic result interpretation along with the 400.2 standards. These are all the different accessories to it. If you want a more complete solution, then we have VLF along with the partial discharge, and it provides CR and DAC waves as well to interpret partial discharges. So this is a complete setup. This is also very customizable. So if you look at all the different options, you can pick and choose based on what you do and what you don't do. So it is a more customizable solution. And in terms of CFL, that's cable fault location equipment, we have a unit that goes up to 40 kV in terms of fault location. It's basically a cable fault location unit. It has a thumb energy of 2000 joules, uh, and it has a couple of different pre-location methods, your arc reflection with multi-shot, your ice and decay methods, and whatnot. And the Premium system is a complete kind of van system that a lot of customers are interested in have bought these units that is more of a complete solution. So if you're a service company that is doing a lot of work for other clients, then this would make sense that you would have a complete one-stop shop. Run out there to the test site, do all kinds of testing, your VLF 10 delta, PD, and then give the results to the customer. So this is more of a complete start to finish solution, if you will. So that's pretty much it for my part of the presentation. I thank you all for joining, and we'll open the floor for questions.
Excellent. Can you hear my microphone coming still, Yash?
Yes, sir.
Wonderful. Just want to double check some pantomiming this last bit for us. So obviously we've concluded our webinar, the presentation portion of the webinar. We're going to be jumping into the Q&A section in just a second. I'd like to remind everyone, if you have any questions, you can enter them there on the left-hand side in the Ask a Question box. We'll try and answer as many of them as we have time for today. I know we're a little light on time. For those of you who are leaving, we would greatly appreciate it if you could take a couple of minutes to fill out our survey there on the right. We'd love to hear what you thought about today's presentation, any topics you'd like us to cover in the future. On that survey is also a field for you to request a quote or a demo on any of the products we just ran through. Our next webinar will be held on May 6th as a part of our renewables testing webinar series. They'll be titled Challenges and Recommendations for Performing Partial Discharge Measurements on Hydro Generators. If that's not your flavor, our next testing tactics webinar will be held on May 16th, titled Testing Self-Powered Reclosers, Trip Savers, which will be presented by Ravi Gupta. As a reminder, we will be sending out a copy of the presentation, a link to the recording of this webinar, and your certificate of attendance, most likely tomorrow, if not 2 business days. So let's jump right into our Q&A. We got tons to go through. I'm going to throw our first one to our panelist, Chase O'Veal. Chase, is VLF a destructive test?
VLF is not a destructive test. The VLF is made to expose whatever issues are already within that cable, whether it be from a termination or dirt or from the manufacturer.
All right, excellent. While I have you, I'm going to ask you one more question here. It's why is a VLF test at 0.1 hertz?
The reason why we test at 0.1 hertz is because DC tests are no longer a valid option. And in order to test at 50 to 60 hertz, you essentially need an 18-wheeler. So what we do is we apply over voltage without applying too much current.
Thanks, Chase. Throwing things back over to Yash. Yash, can 10 delta tests be used for mixed cable types?
It can, but the information that you get from it will not very much be relevant. In this case, you can have mixed cables that will have masked the defects of the other one. So you will have a result, but you would not be able to make much sense of it. And you cannot compare it to the IEEE 402 standard. So the number is pretty much useless, if you will.
All right. Throwing things over to Chase. What is Megger's point of view on partial discharge monitoring of medium and high voltage cables? Does Megger have any products that it can monitor PD?
So Megger's viewpoint on partial discharge monitoring of medium and high voltage cable is that it's absolutely wonderful for localizing where your fault is, especially if you were skeptical, depending on whether it was maintenance or acceptance. It allows you to know exactly where that fault is and what type of fault it is. Megger does offer quite a few products that'll monitor partial discharge. Y'all showed them at the end of the slides. Again, we're happy to give a demonstration on any of those products.
Thanks, Chase. While I have you, what is meant by saying trapped space charges?
So during a DC test, he showed that you don't reverse the polarity. So you apply a charge into the cable, whether it be positive or negative. And whenever you do that, the electrons move. And if you don't discharge that for long enough, you don't relax your cable and move and relax those charges back to their normal positions. If it is not discharged the way that it needs to during a DC test, those space charges, dirt or nicks within the cable, any type of defect creates a space charge. So whenever you apply an AC voltage that reverses that polarity, that space charge can grow. But by space charge, we mean that there is some type of defect within the cable.
Thanks, Chase. Yash, I recently read a paper, which of course I can't find now, that indicates DC insulation, PI, and DAR testing were not providing valid results on medium voltage cables and suggest no longer applicable. Can you elaborate on the effect of PI and DAR have on medium voltage conductors, and if this is still considered an acceptable testing format? If not, why?
So PI and DAR is still relevant in terms of if you are just testing the insulation purely. The DAR is dielectric absorption ratio. For people who are not aware with DAR testing, you basically use insulation tester and you are determining your ratio of 1 minute to your 30 seconds. So that's your DAR ratio. And it is a very short testing. It's not as prevalent or as stressful to the cable compared to a VLF. We are talking like completely different ball game in that terms. PI is a 10-minute test, right? You do your 1 minute to 10-minute ratio in a polarization index. Now that is specifically just to evaluate your polarization on that cable and say whether your 1 minute to 10-minute ratio is good or not. Obviously, you should have your readings increasing because you're now polarizing the cable. So your resistance should be going higher. Now, if it drops down during that 10 minutes, then obviously you have a bad insulation. It's still an acceptable test. There is nothing wrong with it. But understand that this is all what you're doing closer to your operating voltage or typically lower than your operating voltage. So this is not as stressful or as prevalent compared to a VLF test or a T10 delta test in that case.
Thanks, Yash. Going back over to Chase, what is the relation between water tree and TD values?
So the water tree and TD values depend on how big that water tree actually is. If it's been formed for a long time, you may see higher tan delta values within that cable. Again, it's sometimes best to wait for 5 years to begin measuring those if you're going to take data on those, because that allows for that cable to absorb that moisture and those water trees to form. If you're doing an installation test and you see those, you know that from the manufacturer or from the transporter, there is moisture ingress within your cable.
Thanks, Chase. Over to Yash. How long does it take for a termination to fail typically? Is there any likelihood of catching them between maintenance cycles? and I'd appreciate if you could elaborate a little on termination and joint failure issues.
For your question about how long does it take for a termination to fail, typically I would have to be a clairvoyant to answer that. But yeah, there's no way of definitely knowing if you know likelihood of termination failure. That completely depends on the quality of that termination and a couple of different factors, right? There's no one formula that applies all kind of thing. Is there a likelihood of catching them between maintenance cycle? Of course. Now that depends on how your maintenance cycle is set up. If you're doing your 10 mil time PD testing on a regular basis, like every 3 to 5 years, let's say for example, then yes, there is likelihood of catching those failures before they actually happen. Specifically, we have seen a lot of termination or joint failure issues. It's typically relating to the cutback distance. A lot of times, your cutback distance is not enough, or it's too much, or like there's a couple of different scenarios there. But if you have those kind of scenarios, then PD starts happening in those in that semicon, the distance where it kind of covers the semicon and the main insulation, and in that distance it creates a stress point, and because of that stress point the PD starts happening often, and then it kind of eats your insulation over time.
Thanks, Yash. Over to Chase. On slide 35, VLFTD. If we stop the test when we find the cable is where we find the cable is weaker, can we get more time for the procedure and replace the cable? Is this a practical or recommended approach? We throw up slide 35 for us to look at it too. There we go. Slide 35. Go too far. All right, Chase, over to you.
Okay, so if we stop the test when we find the cable is weaker, do you get more time to procure and replace the cable? So a tan delta test is usually done during a maintenance or an acceptance test. So yes, that allows you to. Whenever you find that weaker cable, that allows you to know the life expectancy of that cable. It is ultimately up to you if you want to replace the cable, but all it's telling you is your life expectancy. Are you noticing that there is something that is growing within your cable or not? So if you're the owner of that application and you're doing it during a maintenance time and you feel that it's time to replace that cable and you have the resources to do that right then and there, then I would say do it.
Excellent. Thanks, Chase. And thanks for the catch. So Yash, when you discussed the TNB Malaysia study, you mentioned the cable failed after how many years of service?
I believe it was within 2 years of service that they were assessing it for, but I'll have to double check. But I think that was the time period.
Thanks so much, Yash. Going over to Chase, why does a break occur at the end of a medium voltage cable?
If you mean break as in a termination or a splice, that would be simply put because of, it is the end of your cable. But sometimes that over voltage, if it is the end of your cable, it happens there. It depends on sometimes the manufacturer who provided your kit, who did the termination on the end, and is it able to hold that voltage? And that's what all these tests are trying to determine is why does it break there? And ultimately with a partial discharge test, it can tell you what type of break was in the cable itself.
Thanks, Chase. Going over to Yash, can VLF-CR monitor withstand partial discharge testing be performed simultaneously on all three phases, or must it be done one phase at a time?
So if you are doing a PD test, right? And that's an excellent question, by the way. A lot of people have the same question. When you are doing a VLF, just a VLF, purely pass or fail test, you can hook up all the three phases at the same time and run it along. But when it fails, how would you know which cable failed? So it's a kind of pass or fail that you are willing to test, right? Um, and once it fails, the cable that was like, let's say in the first 10 minutes, phase A failed. What if the phase B and C were supposed to fail in the next 5 minutes? You will never know, like that kind of scenario. So you can't do that, but that's a chance that you are willing to take. Now, about the PD test, the way a PD test works is you get some reflected pulses back and that kind of tells that partial discharge coupler, hey, this is coming from a 500 feet of distance. If you have three phases hooked up at the same time, you will never know where exactly that partial discharge is coming from. You can just see the intensity of partial discharge, but you will never be able to guess where exactly that distance is coming from. So, can you do that? Yes, but you won't have parameters that you can evaluate necessarily that, hey, this is where I'm getting from. You'll just see the intensity of partial discharge and that's it. And your cable capacitance will also go higher, in my opinion, than you if you're hooking up all three phases at the same time.
Thanks, Josh. Chase, can you quickly go over the benefits and disadvantages of online versus offline PD testing?
Sure. So during online testing, the benefit is that you can actively see that you have partial discharge on a live gear or cable that you're testing. The disadvantage is that you're not going to be able to see what type and how bad, what the extent of your partial discharge is currently. With offline partial discharge testing, the benefit is you can localize and then compare your results to see whether it's worth um, swapping out or keeping in service. There really are no disadvantages of offline partial discharge testings except for the fact that you had to schedule an outage.
And I would like to add something to that as well. Um, when you are doing online PD testing, the given thing is that you have to have sensors mounted on that specific cable. So it's a lot of costing involved, a lot of work practices that are involved with it, and ultimately everything comes down to the budget, right? If you have the budget to do it, and online monitoring is something similar along those lines that you have to have HFCTs mounted at every so and so distance or every such termination in that cable, which is not a very budget friendly thing to do again. And given that you have that kind of access to the cable as well, if it's underground and it's direct buried, how would you put HFCTs on that specific cable, right? So that all comes down to the logistics of it, and sometimes it becomes much more expensive and such that you can't really go towards an online monitoring system, and you have to kind of resort to offline monitoring system.
Thanks, guys. I think we got time for one more question. So on slide 45, which instrument are we using there?
We are using a TDM 4540 in that picture. It's a stackable unit. You have the bottom booster module, and I believe there's a 10 delta, VLF 45 sitting on top of that unit. And you have your PD coupler connected here, and then it's going to the cable itself.
Thanks, Yash. So I think we're running out of time for additional questions. If you have any more, I know we have a handful left that we didn't get to cover live today. You can respond to the email that we send out with your copy of the presentation, links to the video recording of the webinar, and your certificate of attendance. That should be going out tomorrow, Saturday. or within 2 business days, most likely Monday if there's a delay. But if you reach out to us on that email, we'll work on answering any questions we didn't get to live with you offline. But I'd like to thank everyone for attending today. After we conclude here, we're going to have our survey pop up here. It's also going to be included in our email. We like hearing how we did during these webinars and how we can continue to improve upon them. And if you have any questions or ideas for upcoming webinars, we're always open to hearing what you guys would like to discuss. But once again, I'd like to thank everyone for joining in with us today, especially our presenter team for jumping on and giving us this presentation. But I'd like to thank everyone and hope you all have a great weekend and to see you again at one of our next webinars. Thanks a lot, guys. Bye.
Thank you, everyone.
Thank you.